Hello and welcome to this series of lectures on discrete time Fourier transform. Before understanding discrete time Fourier transform, let us first try to understand the different types of transforms and where is discrete time Fourier transform among all these different transforms. If you see the summary of transforms, depending upon the type of signal, we have so many types of Fourier transforms. If a signal is continuous periodic, we analyze it with continuous time Fourier series. And if you see this continuous time Fourier series, it is a discrete in nature because there is a summation equation here. If the signal is continuous aperiodic signal, Fourier series we cannot use Fourier series, so we have to use Fourier transform. It is called continuous time Fourier transform because it is used for continuous time aperiodic signals. And if you see the nature of this, since here there is integration, we have it to be continuous in nature. When the signals to be analyzed are discrete time, so when it is a discrete time periodic signal, we have discrete time Fourier series, which again is discrete. And for discrete time aperiodic signals, we have what we call as a discrete time Fourier transform. Now this discrete time Fourier transform, even though the name here is discrete time, this name discrete time is coming from the type of signal, that is discrete time aperiodic signal. But if you see the nature of this signal, it is continuous. So this seems to be contradictory, that here the name is discrete, but actually the nature of this signal is continuous. Okay, so in this series we are going to talk about this discrete time Fourier transform. Now how do we define the discrete time Fourier transform? So discrete time Fourier transform is denoted by this symbol x e raised to j omega. So x e raised to j omega is given by summation n equal to minus infinity to infinity, summation from n to infinity x of n e raised to minus j omega n. So this is the equation of discrete time Fourier transform, and this is normally how we show the pair x of n DTFT x e raised to j omega. If we take the inverse IDFT, we can go from the frequency domain to the time domain. So from time domain to frequency domain and frequency domain to time domain. So this is shown by a double arrow. So it is a discrete time Fourier transform. So this is the equation for this IDFT, that is inverse discrete Fourier transform. If we are given the discrete time Fourier transform, okay, we want to go from frequency domain to time domain, then we can use this IDFT equation, which will give us x of n. There are different notations used for describing this frequency domain relationship. Okay, we can either write it as a direct x e raised to x j omega, or x of ohm, where ohm is the frequency variable. We can write it as x j ohm, x e raised to j ohm, or x e raised to j omega. Now this is the most popular notation which is used, x e raised to j omega. Hence we have used here x e raised to j omega. In all these notations, one thing you have to observe, that it is always denoted by a capital letter. Okay, so whenever you denote a frequency domain representation of a signal, you have to denote it by capital letters, and when you are denoting the time domain signal, you have to denote it by small letters. Now in this equation, we can see that there is a term e raised to j omega, and omega term is continuous function. Hence, this discrete time Fourier transform is continuous in nature. Now, it exhibits a very important property which is called as the periodicity property. What is meant by periodicity property? It is that the spectra which we get of DTFT, that is x e raised to j omega, this is repeating itself after an interval of 2 pi. So the nature of this spectrum is periodic in nature. So x omega plus 2 pi. So after an interval of 2 pi, we will get the same x of omega. That means after a period of after an interval of 2 pi, this spectrum will repeat. That's why the spectra of DTFT is periodic in nature. So this is a very important property of discrete time Fourier transform. Whereas continuous time Fourier transform is aperiodic. Continuous time Fourier transform is used for continuous time aperiodic signals. So the nature of CTFT is aperiodic, but DTFT, which is used for discrete time aperiodic signals, it is continuous and it is periodic. So this is the major difference between CTFT and DTFT. This is the major difference between CTFT and DTFT. So this can be proved why it is periodic. So when you substitute this here, instead of omega as omega plus 2 pi, okay, then using simple mathematics you can separate out these exponential terms. But now it can be seen that this term e raised to minus j 2 pi n is equal to 1. Why it is 1? Because e raised to minus j theta is cos theta minus j sin theta. Okay, e raised to minus j theta cos e raised to minus j theta is e raised cos theta minus j sin theta. If you take cos 2 pi n and sin 2 pi n and put the values in that equation, you will get it as 1. That's why you can compute this result. We have already computed this in the previous numericals and in our previous theory. So this is called as the Euler's identity, or we call it as a Euler's identity. So using Euler's identity and substituting 2 pi n in place of theta, we can compute that this result equals to 1. That's why this shows that this is a periodic signal. There is a condition for existence of DTFT. Since we have seen that Fourier transform has a limitation, that all the Fourier transformable signals should satisfy what we call it as a Dirichlet conditions, and out of that Dirichlet conditions, the final condition is that the signal should be absolutely integrable or absolutely summable. Now since this is a discrete time signal, the existence for DTFT is that the signal should be absolutely summable. So how to write the signal to show the signal that it is absolutely summable? So the summation of this signal from minus infinity to plus infinity mod of n, it should be less than infinity. That means it should be finite value. It should not be infinite. So this summation from minus infinity to plus infinity, it should be finite. That means it should converge. So this is the condition for existence of discrete time Fourier transform. Now this discrete time Fourier transform, we can understand that it is an important type of transform which is used for analyzing a discrete time periodic signals. Okay. Now this transform we will be using for computing the Fourier transform of discrete time periodic signals. For discrete time periodic signals, we will be using this transform, but we will be solving few numericals on this in order to understand how this discrete time Fourier transform. But before solving the numericals, we will also try to understand the different properties of discrete time Fourier transform, which are very important in order to understand or in order to solve the numericals. Okay. So in the next lecture, we will be talking about the different properties of discrete time Fourier transform. Thank you.